So you can put it on slide. Yes, sir.
Is it okay? Yeah. So at the outset, I would like to thank Professor Dadwal and Professor Chandrasekhar for giving me this opportunity to present what advances are being made in the field of radar probing of the atmosphere and ionosphere. And Professor P.B. Rao has already made my life very easy. And if the participants have listened to his talk carefully, I think all basics he has already provided. And 1 hour or 1.5 hours certainly is not enough to do any meaningful job. But what is actually important that I consider is providing some information about this particular field of research. And also what are actually new things happening around us, and what are the challenges that we are facing in advancing so-called the radar probing of the atmosphere and ionosphere. So my idea will be to give you some glimpses. Certainly I cannot cover, it's a very broad field. I think several days would be required to truly cover, but I will try my best. What I will do is I will try to give a quick summary of what Professor Rao has done so that you will understand. And these are the things which I am going to use subsequently. So the radar probing techniques, the current trend. What Professor Rao told is the very fundamental, the very basic building block of utilizing radio wave as a radar for probing the atmosphere, both neutral as well as the ionized part of the atmosphere. Then I will be talking about the progress in recent probing of the atmosphere and ionosphere, and I will cover here troposphere and ionosphere. There will be many things which I will be leaving because for example, meteor science I will be leaving, electrojet science I will be leaving, several things I will be leaving, although ionosphere is part, electrojet is part of the ionosphere, but I will cover only limited subjects so that I can give you some idea that where we are working currently, what are the challenges, how to tackle them, and what are the issues that one can take up from this 1 hour, kind of a talk. So I will be mainly talking about the Bragg scattering throughout my talk. But when we talk about the radar scattering from the atmosphere, we talk about Bragg kind of scattering, we talk about Thomson scattering, we talk about Rayleigh scattering, which Professor Rao already mentioned. So my talk will primarily be focusing on the Bragg scattering, Bragg type of scattering. You all know what is Bragg scattering. And I think somebody raised this question that how the radar's echoes come from turbulence or turbulence scattering. So whether we are talking about noise or we are talking about some signal, what is that we are talking about? I want to tell my views here so that you can understand in the subsequent slides that although atmosphere is turbulent, but actually there is some amount of finite amount of coherence in space as well as time. And that is what actually we utilize for getting the backscatter from the atmosphere. It is not that a particular atmosphere, when it is turbulent, it is not that you will get backscatter at all radio wavelength. No, it depends upon the energy that is contained in that particular scale size. What it means is, if you take a particular atmosphere and you just cut across in any direction, in our case it should be vertical because we are on the earth and we are looking up, or it may be small tilt angle. So along this ray path, if you cut, you will get the refractive index fluctuation, and this fluctuation could be due to humidity, temperature. This is basically nothing but refractive index of the medium. In the ionosphere, it is primarily due to electron density. So if you take, you will get random fluctuation, And if you do the spatial Fourier transform of this particular fluctuation, you will get many Fourier component, which your radar wave vector k, that is 2 pi over lambda, will match. That is called the Bragg matching. So when such matching takes place, then you will have the backscattering from the atmosphere. And this is what is presented here. And this is what most of the time my talk will be focusing on that. There is also called Thomson scattering. And this Thomson scattering is basically applied to the ionosphere when the free electron oscillate due to the forcing by the electromagnetic signal that we are sending, and it will oscillate, and it will, any charged particle, if it oscillates, it will radiate with that particular frequency, and that is what we will be seeing. But then the motion of the electron will be controlled by the environment. For example, the electron will be thermally agitated, so it will give us the thermal fluctuations. If it is moving with the background drift, it will give you the background drift. So all this information we can retrieve if we study the backscatter signal. So this is one thing that is a little special about Thomson scattering. So, but we are not practicing at this moment here, so I will not be covering that. It's another topic altogether. Now, Professor Rao already mentioned about how the radar works in principle, and you send the radio wave, it goes to the atmosphere, where you have the refractive index fluctuations. From there, you get back the signal, where you have the Bragg matching. That is when your wave vector matches the scale, Bragg scale. So, so this is, but then it is, our idea is not to get just the backscattered signal, but we want to derive as many parameters as we can. So one immediate parameter is to know about at what velocity the medium is moving, what kind of turbulence is persisting. So these are some of the parameters which we are immediately interested in. Then any question? Okay. So there is any question?
Yes, sir. Sir, have you changing your slides?
No. I am very much here. I am changing my slide, but is it not changing?
No, sir. We can't see the
No,
slides.
sir.
We are still on the first page of the presentation.
I see. Okay. Okay.
Yeah.
Let me see.
Yes, sir. Please check that. What we can say, the preview section. It might going to work then.
Let me see. Are you seeing a different slide now?
Yes.
Yeah.
You are
Thank
seeing
you.
a different slide, right?
Yes. But sir, it's preview. Please click on the. We can see a notes section also.
Yeah, I'll see. 1 minute. Hold on, please. Where is your screen? Where is the note? Yeah, no note. It is saying. Okay, let me see. I'll just 1 minute. I'll come back. No. The slide is not moving. Should I close? No, it's a note.
Sir, just click on that.
Okay. Oh. Oh. It is not coming. Can you see a different slide now?
Sir, can you please change, because it's showing one slide. Can you please shift to the next slide so that we can see if slide is changing?
Is it changing now?
No, sir.
It is not changing. Here it is changing, but there it is not changing, right?
Yes, sir. I think.
Sir, just click on the presenter view, please. The steps you did last. Show. Start show. Here.
Now can you see, sir?
Yes,
Now. Yes, we
yes,
can see now.
Is it okay?
thank
Yeah,
you.
yeah.
Yes, sir.
Okay, okay, okay. So I need to repeat a little bit here. Okay. So I think I will just come here. What is this screen coming here on the top? Okay. So what I was talking that Professor Rao might have shown you the refractive index fluctuations, the random fluctuation. So if you take a cart vertically, let us say, so you will get random fluctuation. So if you do the spatial Fourier transform of this, so you will get several k vectors. Now, if your radar k vector happen to match with that, that means if your radar wavelength is lambda, then you will get actually backscattering from the lambda by 2. Because you see the phases, you see here the phases which are coming with separation of lambda by 2, they are coherent, they are coming with the same phase. So they will add. So the question is that it is not actually enough turbulent. It has some amount of coherence both in spatial as well as temporal domain. And that is what actually why the atmosphere is giving you the signal. So at some scale, when you go down in wavelength, then you will see at some time you will not see the signal. So that means the spectral energy, the turbulent energy is not sufficient to give you the backscatter. This is what it means. And why, how the turbulence is generated, there are many mechanisms, but at any scale that it is generated, it transfers the energy to the smaller scale. This is what we call the cascade of energy, and this is what we call the Kolmogorov theory of turbulence. Okay, so it has a spectrum, but depending upon the source and depending upon the background condition, this energy transfer will take place. It is not constant all the time, but broadly it is constant. So this is how actually we'll get the backscatter at different frequencies. So I will not cover too much on this. Now, when we talk about that, we are getting signal from the radar, so the radio detection and ranging we are doing, but we are not only interested in the signal, but we are also interested in the property of the signal. For example, at what velocity the target is moving, is it moving with the steady velocity or it is having a turbulent component, whether the turbulence that we are talking about, whether it is isotropic or it is anisotropic. If it is isotropic, in which direction, whether in all directions it is isotropic or it is in a given plane it is isotropic, but if you take a three-dimensional geometry, so it is not isotropic. If it is anisotropic, whether the anisotropy is elongated in a given direction. So if it is elongated in a given direction, why it is elongated in a given direction? So these are some of the questions which come to our mind in order to understand the turbulence and the energy cascade mechanisms. So when we have the target velocity reasonably small, then we send a pulse, we get the return, we send the next pulse, we get the return, we get the next pulse, we get the return. And you can see that the pulse returns are coming. For example, you take the green ball, it is coming here after a delay of 2 tau. Then from the same height, again it is coming. So all this sample, if you gather together, and then you can do a fast Fourier transform, then you will get the power spectrum. This is what Professor Rao was showing in 1 or 2 slides. So this will give you the Doppler power spectrum of the reflected signal. So if the mean Doppler is away from 0, then you know that it is moving with some velocity, and based on the positive Doppler or negative Doppler, you can derive in which direction it must be moving. And from the at least 3 non-coplanar beam directions, you can measure the velocity. But this is always not true, because you see, you are sampling at this rate, but if the velocity is too large, then you cannot sample at this rate. The sampling rate must be much faster. So in this case, what people use is they use the double pulse technique. So you have 2 pulses going in quick succession, then the second pair will go. So the one pair to the next pair is the true IPP, interpulse period, and between the 2 consecutive pulses which are closely separated, so this is giving you a much higher pulse repetition frequency as compared to the other. So this takes care of your pulse repetition frequency, and the other one actually gives you a longer interpulse period. So the interpulse period, by having a long interpulse period, you can go to higher range, so you can avoid the range ambiguity. By having a closer separation between the two pulses, you can have the large PRF, so you can remove the velocity ambiguity. So it's a combination of the pulse pair scheme through which the range and the velocity ambiguity can be addressed. And many times we see that our target is actually moving at a much faster rate. And a priori, we do not know what is the velocity. So that's why these are some of the schemes we have to use so that our velocity measurements are not ambiguous. But that is not all. When we talk about a medium, we come across turbulence. When you assume a turbulent velocity field, then a particular sampling rate is not sufficient to describe the medium. So in that case, what is required is that you should have all sort of sampling so that the temporal space sampling that you are doing, it is not periodic function, it is a aperiodic function, so that all these fluctuation, very short to very large, everything can be addressed within that, so that you will get a very good representation of the turbulent flow field, that is the turbulent energy, how it is distributed, and also the velocity field distributed. You will have a fairly good idea. But then it brings new challenge. The thing is that when you have a periodic pulse, then you know you have a standard Fourier transform and you can get the velocity field, the Doppler spectrum. But here, when you do this, you come across different kind of issues. So those are the challenges, technical challenges somebody can take up and do a good signal processing. Now, so when we have one radar, you have one transmitter, one receiver, it is going the signal is going in a given direction, you are receiving in that particular direction. That provides you some information, but you do not know what is happening in the other direction. The signal goes in a given direction, it gives you the backscatter. But if the targets are oriented in different direction, think that you have several mirrors spaced, put in, kept in space with different orientation, then obviously some of them will satisfy the reflection criteria, some of them will not. So reflection criteria, all of them will satisfy, but for the backscatter, all of them will not satisfy, because the incident ray which is going and hitting perpendicular to the mirror will come back. But the one which is going with a finite angle, that will go to some other direction with angle of reflection. So that, how much is that energy? We do not know. So these are some of the questions that can be addressed using, if you have the multiple receiver. So here is a simple geometry that you have one transmitter and you have two receiver. What is the purpose? Because if you have a radar, you have the finite beam, because the radar is having a dimension, I mean the physical dimension. So your beam width is defined. So within the beam width, whether targets are distributed or targets are localized, that we have no idea. So unless we have fairly good idea about the distribution of the targets, we will not know about actually the turbulent flow field. Even we will not be able to know whether it is turbulence at all. It could be just distribution of discrete target, but not truly the turbulence. But still, you will see there will be a broadening of the spectrum just because they are distributed in space. So it is important to understand this. And the one simple experiment one can do is that you can receive by two spatially separated receiver, so that the phase that you get in one receiver and the phase you get in another receivers are different, and you will be able to pinpoint what is its angular position in the space. So this provides you the hot spots present in the radar pulse volume. So it provides you additional information in the plane in which the two receivers are located. This implies that you need at least one more receiver in the another plane to know its actual position. But if you want to have a precise position, you have to have multiple receivers in space with redundant spacing, non-redundant spacing, just like the spatial Fourier transform. So you will get truly the image of the angular image of the scattering volume. So these are the trends to gather more information. So this is, we are talking about the angular domain, that is spatial domain. But if the target is, so you have a pulse, so pulse has a depth, it has a length. So the resolution is defined by the pulse length. So any signal that you are getting from that particular volume, it is coming from that volume. You don't know whether it is coming from the leading edge or the trailing edge of the pulse, or it is coming from the center part of the pulse. So you do not know that. So if you want to know precisely about the height from where the echo is coming, then you need to resolve that. And that is where you use multiple frequencies, not too much separated. Within the bandwidth of the radar, these several frequencies have to be picked up, and then so that they will cause a small phase difference because their lambdas are different. So here is a case, you have a lambda 1 and lambda 2 very close by. Then from there, because the phases are different, and when you do the cross correlation, then you get the phase difference, and that phase difference can be translated into the location, vertical location of the target. So that means, okay, so by combining the spatial domain interferometry and frequency domain interferometry, one can do a beautiful imaging of the scattering volume, and you will know the hotspots, how they are distributed vertically, how they are distributed horizontally. But it demands a lot of computation and kind of the technique that we need to involve. Now, so these are the things which people do at one place. The receivers are not very much separated, but there is another way experiment can be done, and you can get angular information about the target. For example, if you transmit from one place and receive from some other place, which could be 100 or 200 or 300 kilometers away, so you essentially satisfy a kind of a bistatic arrangement. Okay. Now, when you are transmitting from one place and your bistatic arrangement where you are receiving, you can have either one receiver or you can have multiple receivers. You can have receiver in some other place. So this is basically a multistatic and angular approach to study the atmosphere. So what is the advantage of that? You will know about the anisotropy of the target, that is number one. And you see, when you are looking in the back scattered geometry, you have 1k, that is 2 pi over lambda. But when you tilt the beam, then the k that is responsible is, it is actually the perpendicular to both. It is not perpendicular, it is in between the two vectors, the transmission and reception. In between there is a vector, and that is what is the vector which is responsible for it. So that means by tilting this one, you can have actually several k vectors. You can sample different k of the medium. That is the advantage. And second thing, you will know also about the angular response of the target. So these are the new approach. For example, if you have a bistatic arrangement and you send a plane polarized signal from the transmission, and you receive by cross polarization, two orthogonal polarization, you can measure the rotation of the electromagnetic wave due to the ionosphere, what we call as the Faraday rotation. So if you do that, this Faraday rotation can be written as proportional to the number electron density. So in a way, if you can measure precisely the angle of rotation, you'll be able to derive electron density. This is something very, very important. And this is a very cheap solution for measuring electron density when you have reasonably good targets. And another important point is that this particular technique is very useful when you have the irregularities, because when you have irregularities, we cannot use the Thomson scattering, because Thomson scattering or incoherent scattering is used when there is no irregularity. That's how you measure the background flow field, background medium, electron temperature, ion temperature, which Professor Rao already mentioned. So these are the ways that people can do. Now you have also the multistatic and multi-frequency approach. So for example, you can have multistatic, that means you transmit from more than one place and receive also from more than one place. you can transmit using more than one frequency and receive also more than one frequency. So it's a combination of multiple transmitter receiver and multiple frequencies. And if you combine this information, you get much more about, you learn much more about the medium. So these are the techniques which have been already exploited. And the advantage is that if you have a multi-static approach, for example, take the case of a meteor research. Meteors are coming on their own. So if your geometry is, if you are working with a monostatic system, that means all transmitter receivers are from one location, then only certain meteors will satisfy the reflection geometry. But all other meteors will not do. So if you want to have temporal resolution, you have to use all the meteors coming from all the directions. And that can be achieved only when you have multiple ray paths. That means your transmission, reception should have multiple directions, so that if one ray is not meeting that reflection criteria, another ray is going to meet the reflection criteria. In a way, you are going to utilize all the meteors to achieve the temporal resolution that you need for studying many short time phenomena, such as short period gravity waves or something of that kind, or momentum flux associated with that. So these are some of the techniques which are coming up in the recent years. There are two words which are very popular now, those who are associated with radar activity. They are called SIMO and MIMO. SIMO is single input, multiple output. For example, you can have one transmitter and you can have multiple output, but multiple receiver is called SIMO. This is very simple, and we are doing it, we are practicing it here. But you can have also MIMO. MIMO is a very challenging area, and it is called multiple input, multiple output. So you can have multiple transmitter, multiple receiver. It's computation intensive, but provides you a lot of information. You can have multiple, combination, multiple configurations. So if you have a distributed system, your transmitters and receivers are distributed, you can always configure it for SIMO mode or MIMO mode to derive much more information about the target which we are really looking for at this moment. So these are some of the new techniques which are emerging in the radar probing of the atmosphere, ionosphere, meteor research. So in this backdrop, so we are also gearing up in that mode, that how do we configure our system so that we can have a modular concept, we can have transmitters individually controlled, we can have receiver as many we want, we can have receivers where we want, and then so that we can put all the information and compute the backscattered signal and learn more about the signal. So this is the kind of a concept that is emerging, and we are also following the same thing. You can see here the Indian MST radar, which was set up in 1993 and made fully operational, for which Professor Rao has mentioned. This has been totally revamped, and each antenna is now fed with individual transmitter of 1 kilowatt each. So 1024 antenna is fed by 1024 transmitter of 1 kilowatt each, total power amounting to about 1 megawatt. Earlier, the power was about 2 or 2.5 megawatt for all practical purposes. The power has come down peak power wise, but the advantage here is that the transmitter is sitting right below the antenna. So you are avoiding a lot of losses. So the kind of loss that you had earlier, about 3 dB or even more, that loss is avoided. So this is that result I will show you, that how much gain we are having. And then we have multiple receiver. So all these receiver data can be used for spatial domain interferometry and imaging. You can do imaging of the atmosphere, you can do meteor, you can do ionosphere. So this is the kind of a configuration. You can use it in different modes. These are the subblocks, and one can use in different way as user decides. And currently we have 18-channel receiver functional, and this can be upgraded to 64 channel, and you can use different pulse width and different beams so that you can measure whatever you want to measure. Now, the gain that I want to tell you, that here These are the power spectrum which Professor Rao has already shown. Here is a comparison. The blue line is the earlier system, the black line, the red line is the present system, and you can see the improvement in the signal to noise ratio. This is actually not the signal to noise ratio. This is the detectability, which tells you that how reliable the signal is. So you can see signal going up to 20, about 25, 26 kilometers. So you can detect signal. This is the kind of improvement that you can see from an active array system. Because it is active array, you can choose any module or modules, and your lower height coverage you can improve. That means you can start from very low altitude. Okay, and here is an example. And these particular observations were made with 37.5 meter resolution, excellent resolution. Otherwise, the height resolution is about 150 meter, or you can do even worse resolution. But 150 meter resolution is a very standard resolution that we use. But in this case, it is 37.5 meter resolution, and you get the information about winds and turbulence as a function of height and time. So this is another one wherein you can study the boundary layer. You can go down to lower altitude by using a smaller array, that is 16 by 16 array. And the lowest height that you can capture is 600 meter, and you can go up. This is something very, very different. Generally, we use at a time one beam, but in this case, we can configure the system because it's an active array system. We can configure the system to have 4 simultaneous beams looking in 4 directions. What does it mean is that you don't have to switch the beam as a function of time. You don't have to lose that time. If you want to capture a very short, the fast phenomena, then you can have this. So in one go itself, you have the measurement. Okay, so you have 4 beams in 4 directions. You can take this data and then do the processing, and you can get. So what is achieved is, in 10 seconds, you can derive winds and turbulence. 10 seconds. So all fast phenomena like the wind gusts or turbulence, such kind of, or any phenomena linked with convection, those things you can study in greater detail. So this is the direction it is moving. This radar, although it's 53 megahertz radar, but it can also detect the hydrometeor signals, the signals coming from hydrometeors. They are we call precipitation echoes. So how these precipitation echoes are changing with time, what is their Doppler, whether they are falling, they are not falling, all detailed information you can derive from this particular thing. One important measurement which the radar is capable of, with a lot of, I should not say limitations, but one has to be very careful in estimating turbulence. So this is the turbulent intensity, and all other parameters which Professor Rao has shown, the AD dissipation rate. So these are very, very important for aviation, dispersion of pollutants, and also in the cloud physics. For example, if you have large turbulence, what it is going to do to the cloud processes, cloud microphysics, and also the precipitation. So these are some of the things which are very important in the atmosphere. So here the radar gives a very good information in terms of height and temporal resolution, but radar has its own limitation in certain respect, because what you measure is you measure, but then we have to understand how these instrument functions are playing a role in the measurement. For example, when you have a finite system, it has aperture, it has some finite aperture, so your beam width is defined. So when your beam width is defined, so what will happen, due to the finite beam width itself, there will be the component from the main wind, and that will actually contaminate the measurement of turbulence. And if you look at this equation, the turbulence, what is you are aiming to estimate, is actually sigma observed, the sigma square observed, minus these are the correction terms. What are the correction terms? The correction terms are due to the finite beam, and if you have a shear, wind shear, that also will contaminate here. Then you have all the time atmospheric waves. So these are the contaminations. So these contaminations have to be removed. So theoretically, one can always derive some equation for removing this contamination, or what you can say non-turbulent component in the measurement. But it is not always true, because you cannot use a steady function and then subtract, because it has been seen practically that when you do that, many times you come across negative values. But sigma turbulence cannot be cannot be negative. It can be a very small number, but it cannot be negative. That indicates that the correction which we have applied certainly is not correct. So these are the challenges, and here is the figure to understand this process. For example, if you have a finite beam, you see this is the radial velocity that is on the bore side, but you have also finite beam, so you can have also the velocity that is delta f coming this way and that way. So these are the contamination. These are the non-turbulent component which need to be subtracted very carefully. Then only you will get the turbulence. And this turbulence has a lot of application in terms of pollution research, in terms of cloud physics and rain microphysics. And of course, when you tilt it, then you have some other thing coming, the mean wind coming, shear flow is coming into it. When you are looking vertical, you have the Braun-Weisel oscillation, you have the waves coming in. So in different direction, you have different contamination. So far as the waves are concerned, if you are not making measurement for a long time, I mean for one set of measurement, if you are not dwelling for a long time, you can possibly eliminate the effect of waves. But the other components such as the beam broadening, shear broadening cannot be avoided. So this has to be done. So that's why people are coming up with dual beam width or dual frequency observation, so that this particular problem can be mitigated. So these are the challenges which one has to work out. Now, since we have the active phase array system, always you can configure your system with multiple receiver or multiple beam directions. In a way, you will get the azimuthal, the scatter field. And from there, you can derive both wind field as well as the direction. And you can see also the anisotropy that is already present in the system. So you can do this, it is all automated. So the beams will be placed automatically by the radar controller. It will make the measurement, and then you can derive all the things. So you will get as a function of height, how the refractive index field is distributed, and how the turbulent is distributed, and how they are oriented, whether they are having any orientation either along the mean wind or across the mean wind. All these things you will be able to derive. There is also another technique. This is all we talk about, the Doppler beam swinging technique, that you put the beam in a given direction and you get the Doppler measurement. And the Doppler is not just a simple line, but it is having a width. This is what actually provides us the turbulence. But there is another way that one can derive some of these parameters, such as winds and turbulence and anisotropy. If you use a particular transmitter looking up, and then you have multiple receiver at the ground, which is actually multi-receiver experiment, and you do the cross correlation among the signals, then you derive actually the autocorrelation and cross correlation functions, and from there you can derive the wind, turbulence, anisotropy, all these parameters. Yeah. So I will come to the other field, the equatorial plasma irregularities. Equatorial plasma irregularities, as seen by radar, is very well summarized in this particular view graph. This view graph is generated by the well-known Hicamarca radar, which operates at 53 megahertz from Peru. And you can see these are the called radar plumes, which represent the equatorial plasma bubble. I will come to that, what is equatorial plasma bubble. And this is the bottom side, you have sharp gradient, and there you have the plasma irregularities. See, these irregularities are very relevant for our communication, satellite-based communication and navigation systems, such as GPS. In our case, IRNSS also will be equally affected by this kind of irregularities. These irregularities occur during night, that is soon after the sunset, and they can go up to early in the morning. But during daytime, you have also other classes of irregularities which are there nearly about 100 kilometer. We call equatorial electrojet, pretty close to your place in IST. So there are observations being carried out from SPL Trivandrum for quite some time, so many years now, and we have fairly good idea about that. There is one echo which continues to be puzzle. I will be talking about that. This is the call 150 kilometer echoes which Professor Rao mentioned, and it comes like a necklace having clearly showing solar zenith angle dependence. So I will be talking here two topics today. One is the puzzle, the 150 kilometer echoing puzzle. These echoes occur during daytime, and you can see in this particular map, this is height and this is local time. These are the echoes which are coming from the equatorial electrojet, because at the electrojet you have a strong current, and the strong current can generate plasma irregularities. Okay, there are two mechanisms through which the plasma irregularities can be generated, and they are all well known, called as two-stream stability and gradient drift instability. But this has been investigated quite a lot, and but this is the one which I am talking about. This is weaker than this, certainly, but the signal intensity of this also is about 40 to 50 dB above noise, so not very small. And these are very strong. This could go up to 80 or 90 dB above the noise. These echoes were discovered by the Hikamarka radar in 1964, and nobody paid attention because there were much bigger problems, such as electrojet, which Professor Rao mentioned, and also what was known those days called equatorial spread F. And now people are focusing very much on that from application point of view, that is for communication and navigation. The interesting part is that what we know about the plasma irregularities in the equatorial ionosphere, also in the mid and high latitude ionosphere, we know there are some known plasma instabilities, and those plasma instabilities grow by taking energy from the system. So the free energy comes from some source. For example, you can have strong current, you can have strong electric field, you can have density gradients. So these are the known free energy sources for making the plasma unstable. But this is a case where you don't have strong current, you don't have strong electric field, you don't have gradient. That's the puzzle. Then why do we get these echoes during daytime? That's the question to be answered. So, and then you are getting signal as large as 40 dB above noise. So the question is that what causes enhanced electron density fluctuations? Because when we talk about electron density fluctuations, electrons are always fluctuating, the density is always fluctuating, and this fluctuation can always be there due to the thermal agitation, due to temperature. Okay, so they are called thermal fluctuations, and from thermal fluctuation we get very weak signal, very feeble signal. They're almost close to noise, very little. So you need to have a very powerful radar system to detect them, and that's how Hikamarka radar, Arecibo radars were born. But these echoes, what we are talking about today, they can be 40 dB above noise, so smaller radars can detect them. So the question is that what causes enhanced electron density fluctuation? What is the source of the free energy? What is the plasma instability process that is causing 40 dB signal enhancement? These are the fundamental questions that we need to address. But that's not the end of it. The question is that these echoes, they come beautifully with Cauchy periodicity. So what causes this Cauchy periodicity? In the atmospheric science, we see anything periodic, we talk about a wave. And generally we talk about some wave in the atmosphere. Could be gravity wave, could be any other wave. But here we will see that what are those. So the question that was lingering in our mind is that what creates these echoes. So after several years in 2016, something which is workable, which is to some extent acceptable came out. It's called photoelectron induced enhanced plasma waves. Why this has been received well, because this is the region that is about 150, around 150 plus minus 20-30 kilometer. There in that region you have the maximum production of photoelectrons. So photoelectrons are produced during day by the solar photo energy, and since you have more number of photoelectrons, so that was a logical choice. But the question is that how these photoelectrons are producing this enhancement of the plasma fluctuations. So the immediate answer, not answer, but the guess is that if you take the spectrum of the photoelectrons, then you will see there is not a smooth function. There are dips, there are bumps. So that means the energy distribution is not a simple function. It is having bumps, it is having dips. So then if this kind of distribution happens, then you can have plasma instability setting in. But the question that remains to be answered is that whatever bump, whatever dip you have, whether you can work out a plasma instability or a energy transfer mechanism through which the plasma waves can be enhanced to a level of 40 dB above the thermal noise. That's the question to be addressed. So this is where actually things are stuck. But the immediate recommendation which came in is that if the UV flux is the sole cause for the photoionization production, certainly these echoes don't occur during night. So definitely it is day. So the immediate suggestion was that it should be tested. If you plot the echo strength as a function of UV flux, then you may get some answer. So that was the immediate solution. But there was another challenge. These photoelectrons are produced at mid latitude as well as high latitudes. But why these echoes don't occur at mid latitude and high latitude? This question also has to be answered. So at this moment, we know for sure that these echoes don't occur at mid and high latitudes. So there are much more than the photoelectron flux or the photoelectron induced enhanced plasma waves playing role in this particular echoing phenomenon. So a clarification came from our own experiment from Gadanki, and also we have used data from Kota Tabang, Indonesia, so that we have a better picture. And what we have shown is that if the UV flux is decreasing, the signal intensity is increasing. So there is an inverse relationship. So this particular result has challenged the basic, the guess that it should be proportional to the UV flux. That means it is not simple UV flux, but there is much more physics happening here. Then even during the similar UV flux condition, you can see on one day you can have very strong signal. The next day, you don't have that. For example, in another year, you have 2 consecutive days, you have 2 different signal conditions. So that means even for the similar UV flux condition, you have different signal strength. So there must be something else happening. So I think it is the energy transfer mechanism, it is the enhancement process of the plasma waves, and maybe to some extent, the atmosphere and atmospheric waves play a role. So in a way, it's a very, very complex process, including photochemistry and wave particle interaction, and also the plasma waves at that level. One more experiment we conducted, it's again unique experiment done from Gadanki, is that we have 2 frequencies, that is 53 megahertz and 30 megahertz, located in the same place. We looked at the same volume of the ionosphere by the 2 frequencies, and we found completely different result. On the left, you see the 30 megahertz result, and on the right, you see the 53 megahertz result. Very different, and their behaviors are very different. So in a sense, this particular experiment has brought out that there is a wavelength dependence. And from our past, we know the wavelength dependence often we found to be associated with the turbulent process. And if this particular result is true, which is yes, then we must be also thinking in that direction that plasma is not unstable at particular K, but it is having a K spectrum. And not only the K spectrum, but it is again the larger lambda or smaller K, which is having more power than the than the larger K. But this is something very puzzling. This is again a new finding that you can see a lot of fine structures. It is like a ball going up and down, up and down, up and down, okay, with beautiful oscillation, okay. So what is this? What is this high resolution? This resolution is only tenths of second. So we cannot imagine any atmospheric process such as gravity wave to behave like this, because the Braun-Weisel period at that particular height is about 7.58 minutes of that order. So certainly any periodicity which is of that order or even more can be viewed from a gravity wave perspective. But if anything, any such perturbation which is coming so periodically with a period of about tenths of second is certainly not related to gravity wave, something else. So the speculation is that the band structure result from, excuse me? Excuse me?
Yes, sir, you can continue.
Okay, fine, all right.
That
So,
some.
yeah. So the speculation is that the band structures result from a resonance between the upper hybrid frequency and the electron cyclotron frequency. This is where we stand. So in summary, the physics is very rich and complex, and possibly the 150 kilometer ecos pose the most challenging ionospheric science problem today. So I move to the next aspect of the same thing. These particular ecos are not just curiosity to us. These are very faithful representative of making measurement of some background parameters such as electric field. See, when we talk about ionosphere, electric field is a very, very important parameter which drives the ionosphere, okay, the electrodynamics. So these ecos can be very faithfully used because you get the Doppler shift, and this Doppler shift you can translate into E cross B drift. And this E cross B drift we have compared with the satellite observation, and we have found very good agreement, in fact, very good agreement between the two, implying that these ecos can be very faithfully used for measuring electric field continuously. The beauty with the radar is that you can get information continuously for a given location, unlike satellite. So finally, what has come? We have got all the observations for several years, and we have come up with a model. And this model actually is the E cross B. This is nothing but the electric field model for the Indian longitude. And we have put the electric field measured using this, and also the electrojet current, and we have developed a model, and which is already published in JGR, and this is the model which should be utilized for all practical purposes for the Indian longitude, because other models which are existing, they don't work. And if you compare this model output with the satellite measured, for example, synopsis observations for our longitude, you get a very good agreement. So this is giving some kind of a qualifier that these ecos can be used for practical purposes to study the equatorial electrodynamics. So another 5 to 10 minutes can I take? Okay. So the other one which I was talking about, the equatorial plasma bubble. So this is nothing but the low density plasma. It is actually the plasma bubble means low density plasma, just like air bubble. Okay. So when this air bubble goes up, this is not air actually, this is a plasma bubble, low density plasma. When they are generated, they go up. In that, the motion become nonlinear. It generates a lot of plasma structures and irregularities, and those structures and irregularities are responsible for scintillation of radio wave coming from the satellite. Okay, these are not only important for satellite-based communication and navigation, but they are also important for many applications such as over-the-horizon radar. See, where we use the HF frequency and then use the refraction mechanism to monitor beyond the horizon. Okay, so these are the things which are highly detrimental for both radar applications as well as communication. Now, these irregularities as they are seen by the radar, if you see that what is their counterpart in terms of the plasma depletions or the density, whatever you call it, then you find at the bottom, this is actually the air glow depletion. Air glow depletion is nothing but representation of the plasma depletion. And you see a very good agreement between the two. So it is essentially representing the depletion, but when you observe the radar echoes, you need to know in what state you are measuring. So when you measure the velocity wheel, you will be able to know about in which state you are measuring, because the depletion, whether it is a fresh depletion, whether it is a old depletion, just moving through your field of view. There are a lot of interesting things happening nowadays. So if you go by the conventional wisdom, so far as the understanding of this particular process is concerned, after the sunset, you have the bottom side very sharp, and if you have a perturbation, and that perturbation can grow by taking the energy from the gravity-driven current, and this can grow, and as it goes up, then it becomes nonlinear, and it nonlinearly moves up. And observationally, it has been found that these plasma bubble, they can start from about 300 kilometers and can go as high as 1700 kilometers. That means you have a big, very tall channel of plasma depletion inside. The plasma is depleted 90 to 95% or even more. So very few plasma, very little electron density will be there inside. So that means you can understand that if the satellite signal is passing through that versus the signal is passing in the neighboring region, these two signals will be very, very different. And the wisdom is that the Rayleigh-Taylor instability is responsible for this. But question is that this has been, we are talking for many, nearly 50, 60 years, we have been talking about Rayleigh-Taylor instability. But question is that what remains? The question is that if you think that the Rayleigh-Taylor instability alone has to take off as an instability to make the ionospheric plasma unstable, it will take very long hours. Okay, by that time, the ionosphere itself will stabilize the system, but it does not happen. The question is that the background ionosphere must be providing some condition which is very conducive for the Rayleigh-Taylor instability to take off in a very short time. So one very important observation came in from Kwajalein Island. This is a defense radar. It's an incoherent scatter radar. And so this observation is done through the scanning. So you can scan the radar beam, horizontally. Then you can find there are corrugation, there are undulations at the bottom of the region during the sunset time. And this corrugation or this undulation is growing with time, and eventually you can see the bubbles are taking shape where you have the trough, the electron density trough. This is eye-opening result. And so the question is that what is this corrugation? And what is the source of this corrugation? Can we capture this corrugation well in advance so that we can have a meaningful prediction? Because plasma bubbles do occur, but they don't occur every day. They don't occur every place every day. So there is a lot of spatial and temporal variability, and that's the question which need to be addressed so far as the prediction and the weather of ionosphere is concerned. And this is where we stand. So here, there's a debate going on that the upwelling that we have seen just in the previous slide, so this upwelling actually is growing. The question is that whether it is the Rayleigh-Taylor instability which is taking off from this undulation, or the upwelling itself is having electrodynamics that will grow to a point, do a handshaking, and Rayleigh-Taylor instability will take shape and it will take it non-linearly, go up in a short time. Okay, this is the question that is now lingering in the mind of the scientist, that this needs to be debated, that whether it is the upwelling in the beginning and then the Rayleigh-Taylor. Because the question, the current wisdom is that the Rayleigh-Taylor instability will grow when the ionosphere will go to high altitude due to the pre-reversal enhancement of the zonal electric field that happens during evening time. But it has been found that it is not true, because the electric field, that reversal, before the reversal, the enhancement takes place in a larger longitude zone. But plasma bubbles don't occur in the same longitude zone. It occurs only in a given longitude, in a given small longitude zone. So the question arises is that particular electric field, while providing the background condition, it does that, but it does not play a decisive role whether the plasma bubble will occur or don't occur. There is some other element which needs to be considered. That's where the background seed perturbation or something like a large scale wave structures are being talked about. And this is the cartoon that is actually representing that you have the pre-reversal enhancement in this longitude zone about 3000 kilometers, but you can have a large scale wave structure, and these large scale wave structure can grow and generate plasma bubble eventually. That's the hypothesis. We need to test this, however. Here, I will bring some finding from our own place. This is a Gadanki ionospheric radar interferometer, which we have set up in the same place. It operates at 30 megahertz. It's a low power system, but its capability is enormous that it can be, the beam can be tilted up to plus minus 50 degree. So about 100 degree angular space you can see. So it's kind of an imager. If you do this, then you see that at different angle, the echoes you are getting. And then when you put them in a zonal, excuse me, somebody is talking. Yeah. So if you put it in the zonal plane, then you can see that these structures are moving from west to east. And these are the structures. They are moving. Now, if you see with time, you can see their location and you will be able to find out where actually they are generated. This is something very, very important because they are not generated every day in the same place. So if we can find out where they are generated and link it to the background ionospheric condition, this will give us a clue as to how to handle this problem so that we can have a better prediction, so that we can really do the weather forecasting. Weather, that is ionospheric weather. So the question that I want to come back again. Okay, so this one, this is the question that I'm coming back. That is the seed wave I mentioned in the previous slides, that there is a seed wave. Somebody is talking continuously. I think he should be told not to talk. So
yes, sir. Sorry for that.
Yeah. So this is the seed wave hypothesis. We need to test if we have to move forward either to
Santosh Kumar sir. Santosh Kumar sir, can you please mute your mic? Sorry sir, I think now you can continue.
Yeah. Okay.
Sorry.
So the question is that the hypothesis that I mentioned about the seed wave, okay, it could be gravity wave, it could be anything for which we do not know, but the first idea. I think you have a controller, no? Dr. Jayati.
Yes, sir.
You should mute all the participants. You should mute all the participants.
Yes, sir, I agree. I'll just ask Chandrasekhar sir to do it. He's the host actually. I don't have the control. I'll just talk with him. I'm sorry. Santosh Kumar sir, can you please I apologize, sir. 1 minute. I'll just have a word with Chandrasekhar sir and I'll be back.
పడిపోయిన తర్వాత ఇంకా ఒకదాని కూడా చెయ్యి తర్వాత కాలు ఇరిగిపోతే అదే నీకు అదే చెప్పపోయాడు అదేమో లాస్ట్ టైం ఇది అయిపోయి నేను
So,
ఇదంతా అయిపోయి నేను పట్టించుకో.
what is the name of the person?
లేదని అనబ్యాంక్ మంది
Please mute Santosh Kumar.
Santosh Kumar, B. Santosh Kumar.
అన్ని కలుపుకొని
I have to go to participants. Okay.
కదా ఎవరు పడతారంటే మేమే చల్లి ఇది ఆఫీస్ ఎవరు ఇది బాధ ఈ ఆఫీస్
No, this sharing of. Yeah. Name, what is that?
అలా అది తిన్నాడు కదా అది వాడు తిరిగొస్తుంది బాగుంటుందా లెటరింగ్ చేస్తుంది అసలే వీడియో అడిగి చెప్తాను. నాకు ఎందుకంటే ముందు ఎప్పుడో చేస్తే లెటరింగ్ చేసింది. ఒకసారి అడుగుతా, నువ్వు గాబరపడతావు. నేను మామూలు లెటరింగ్ వద్దు నీకు ఇది పర్లేదు, లేదంటే డయేరియా గట్ట ఇదైతే మన ఈ కొబ్బరి బండ పర్లేదు కానీ తిరిగి వస్తుంది కొంచెం లెటరింగ్ చేస్తుంది. ఇది ఉన్నాయి ప్యాకెట్లు ఉంటే పర్లేదు. ఏరియా కాదు విరోచన అవుతాయి. ఏరియా అంటే దానికి మాత్రలు ఇచ్చేది 3 వరకు వాడొచ్చానమ్మా. ఎక్కువ విరోచనలు అయితే అదే డయేరియా. ఎక్కువ అయితే నీకు విషయం చెప్పనా, ఇదేనో లోపల అయితే గట్టిది.
He is killing time of each and every participant. So please remove him. Please remove him so that the presentation should proceed.
Yes, sir, I agree with you.
Now it's done. Yeah.
Okay.
I apologize to all the participants and Patra, sir.
Yeah. I think simply just remove him from the list. It's not, I think he does not deserve. So, okay, coming back to this seed wave, which the hypothesis has come in the recent time. And, but really, if we have to proceed for understanding the day-to-day variability in terms of space and time, and so to proceed to the next step, what we call as the forecasting in the sense of weather, and this particular thing has to be tested. Nothing worse here. Yeah.
No, sir. Actually, we like made him out of the meeting, and then he joined again.
But how he can join? He cannot join like that.
Yeah, I've removed him.
Okay. So the here, this is actually a old hypothesis in a sense that people have been talking for quite some time that the troposphere can generate varieties of gravity waves, and these gravity waves can propagate up depending upon the conditions. So some of the waves will be propagating in some condition up, some of the things will not be able to go. So there will be a day-to-day variability. So this was dumped on the gravity wave, that the day-to-day variability most probably depends on the day-to-day variability on the wave propagation itself. So this is what actually was going on. So we are trying to test this hypothesis that whether the waves that we see there, we do not know they are atmospheric gravity waves or not, because we do not have full control on the atmosphere itself, neutral atmosphere. What we are monitoring in the ionosphere is the ionospheric parameter, some kind of a wave structures. And left side, you see, these are basically the modern digisonde observations. Digisonde is nothing but the HF sounder, which Professor Rao mentioned. And you can see there are wave properties, which are these phase slopes, which are showing the downward progression is basically the propagation of the wave upward. So from there, if you use the dispersion relation, and you can get actually the horizontal wavelength, and this is what we need. So these horizontal wavelengths have been found to correlate extremely well with the interbubble spacing. So, but then the question is that this is only a kind of a direction in which we are getting motivated that yes, these and these are related. But this alone does not decide whether a plasma bubble is going to occur or not. Now, the second part, which I want to bring to you, is that, see, from these observations, since I already mentioned that you have the scanning observations, you are able to know where the bubble is generated. So if you use its back trajectory, for example, some of the bubbles are not generated overhead, but if you go by the back trajectory calculation based on the velocity that you derive, you will be able to terminate them at the solar terminator. Okay, so the solar terminator, at the solar terminator, they must have been generated, and that location you will be able to find. And if you do, for many cases, you will see that they are actually, this is plus up to 400, that means eastward, and this is going up to minus 2800, that is westward. Because most of the bubbles which are generated west of Gadanki, they will be coming to us because the bubbles are moving with eastward velocity. So most of the bubble that we will be seeing is basically close to Gadanki and west of Gadanki. That's how it is. And you can see the location at which they are generated on a day-to basis is varying very much. And there are also gaps. So if you go through a detailed analysis, then you find that actually some kind of wave, and we found that up to about 2,500 kilometer horizontal wavelength waves are actually playing important role in addition to the short waves which are of the order of 200 to 400 kilometer. These 200 and 400 kilometer always have been classified under the gravity waves, but 2,500 kilometer have not been thought of so far because no plasma bubbles are seen with this kind of separation. So the location now we are able to find that at the origin. So if we have this handle, this large scale wave process, whatever has been hypothesized, that can be tested. And if it is tested, then we need to have a next level of experimental verification by putting up spatially the sensors, especially in the longitudinal zone, so that you can confirm, yes, indeed, the background conditions were different at different longitude. And that will confirm the large scale wave hypothesis. This is another finding that has come from the scanning observation of this particular radar, that all the plasma bubble that we see, they occur between the E region sunset and F region sunset. E region sunset and F region sunset differ by about 30 minutes. Okay, so all the uncertainty remains. This kind of uncertainty will continue to be there between the E region and F region. But then, but from our past experience, we find from the large scale wave process, you will be able to get this signature much well in advance, typically around 3 o'clock to 4 o'clock. So this will give a reasonably good forecast for the plasma wave. Having done all these things, so we are all talking about the post-sunset development of equatorial plasma bubble, and we are taking the relative instability as the main instability process. Now we are bringing in the upwelling into the process to do the handshaking, but where the upwelling will take place, that depends on the large-scale wave process, which is already at the background. The origin of the large-scale wave process is absolutely unknown. Whether it is gravity wave, whether it is sporadic E, it is not at all known what it is due to. But all that we have talked about, this particular well-known phenomena, which has been there like a challenge for many years, if we have done something on it, we have not done anything about the second one, which is at the bottom panel, that what causes the post-midnight plasma irregularities. Sunset has happened much before. The conditions are not at all prevailing there. So what is causing this, causing the plasma to become unstable? So this is something which is very important, very challenging, and both in terms of experiment and simulation and modeling, in order to understand the near Earth space environment. Of late, a new observation has come from Hikamarka. This is not yet published. It is just a preprint kind of paper. You can see the plasma becoming unstable up to 2,200 kilometers, well above the F region. Actually, it is the plasma density is very low. The density gradient is negative. Actually, no plasma instability of the kind that we have talked about so far can be unstable there. Okay, so this must be a different spectrum of plasma irregularity that must be working there. Okay, so in a way, the radar has been used very thoroughly, very extensively, with multiple ways to understand our atmosphere and ionosphere, and I think it will continue. It has already created several puzzles and will keep us busy in understanding these processes using radar, using in situ probes by rocket and satellite, and also other ground-based experiments. So with this, I stop here. Thank you.
Thank you, sir. You extended Rao sir's lecture and continuation with the Bragg radar scattering. Your session was indeed very, very interesting, topped by simple diagrams for every topic explanation. You also gave insights on emerging trends, CMO and MIMO. You also explained the turbulence intensity, equatorial plasma instability, and also shared about some experiments at Gandaki. I thank you for being here, and I also express on behalf of IST our gratitude for your acceptance in this session. I also thank all the participants for their presence and hope that they have a lot of takeaway from these sessions. And if participants have any questions, I request them to kindly put their questions in the comment section, the chat section. Sir, we have one question from Daniel Simon, sir. So how the signal detectability is measured?
Okay, so the signal detectability by definition itself, see when you see the signal, I am telling that the definition that we are using, so you are getting the backscattered signal as a function of time, and then when you do the Fourier transform of it, you get the Doppler power spectrum. Now in the Doppler power spectrum, there will be several peaks, lot of fluctuation, lot of, and then if you have signal, you will have a definite some peak. So whichever peak is there, whether it is out of fluctuation or signal peak, there will be a peak power spectral density in the entire spectrum. So if you take that number and divide that by the standard deviation of noise that you have on the background, then the ratio of this is called the detectability. Okay, so anything which is more than 3 is supposed to be a detectable signal, but it all depends upon what kind of processing you have done. You have not done any processing, 3 dB will not give you a very good detectability. It will give detectability, but it will not be reliable. So the Professor Rao, I think, was mentioning about the coherent and incoherent integration. So if you do some amount of incoherent integration, the noise fluctuations can be brought down. In a sense, the signal power, whatever the power spectral density, will remain at the same location. So if you divide, you can increase the detectability. So by increasing the incoherent integration, that is, you can average several power spectrum, then you can improve the detectability and detect the signal reliability.
Thank you, sir. Then we have another question. Is riddle available only till 150 kilometers? Is it is the riddle only associated at 150 kilometer?
Yeah, I think there are several puzzles earlier, okay, but then many of them have been understood quite well, okay. And basic processes, when you talk about equatorial electrojet, basic processes about the plasma bubble, I think by and large we know. So there are no major puzzle. But when you come to the daytime 150 kilometer echo, as we proceed, as we probe more and more, actually the riddle become a bigger riddle, because it brings new component into it and challenges the old hypothesis and old interpretation. Okay, and the very fact is that in that particular height region where things are happening, you do not have a free energy source. I should not say it is not there, but no known free energy source, because we are familiar with certain sources. So those sources are not there. So the question is that it is important to discover the unknown free energy source for the plasma instability. And that's why I think it continues to be a riddle.
Okay, thank you, sir. Those were the only questions.
Yeah.
And yeah, the participants are writing that the session was very interesting and informative. Indeed, it was. So thank you, sir, for your valuable presence.
I just want to tell 1 or 2 sentences to the participants. What I presented is actually a very advanced level of understanding, and it is not easy to capture things just with one slide and couple of sentences. But what I try to do is that there are many, many things where this country is advancing and contributing to the understanding of a particular process internationally. Okay. Second, that means we have certain capability to address these issues. There are challenges in both in the hardware domain, software domain, signal processing domain, plasma physics domain, and computation means all these artificial intelligence, machine learning, then some kind of signal processing, image processing, all these areas. So there are a lot of opportunities for many, many faculties, many students to participate and learn and sharpen their ideas. Okay. And so I wanted to give that impression to the people that going back home, what they take is that there are some challenges which possibly we can take up. That's my intention. And if they have got something out of it,